Hi, everyone. Welcome to the fifth lecture of our Bootcamp. On Friday, Friday's our last lecture. They're calling for snow this weekend, and it looks like the university will be open on Friday. But if for some reason things get shifted around, if the university is open, I'll be here. If there are any questions about that, or if they have a delay, I'll get in touch with the university and I'll email you guys. But right now, it's not supposed to get bad until Friday night, so I think we should be okay. Anyone have any questions? Starting off? All right. So today's lecture is a lot about data cleaning and data manipulation, especially within the context of data frames. And I'm going to try to show you some of the features of R that have really changed the language recently. And at least from my observation, have caused R to become a lot more popular recently. So when we'll start off talking about strings, and when there's basically two different kinds of data in a very broad sense that you can have stored on a computer. There's binary data, which it might be data that's compressed or data that's only readable by certain computer programs. And if you go to try to look at it with like a text editor or some other simple program, it will look like garbage. Then there's very broadly text data, which really just means that if you open it up in a text editor, like text edit on Mac or Notepad on Windows, there's some discernible structure, and the data that's there is at least readable by the human eye and makes some sense. And so there are a lot of different ways of getting text data into R. A lot of if you are dealing with someone or an organization that regularly provides data, it'll be structured, and so it'll be in a CSV, like we talked about last lecture and a few lectures before, where you can just use like functions like read.csv or read.table. In that case, you avoid a lot of problems because the text data might be marked up in a way to structure it, but you don't have to actually worry about that structure. But a lot of the time, you'll see text data that it might be structured poorly, or you might have like downloaded. People distribute data a lot in Excel and in Excel workbooks, and so with Excel workbooks, sometimes people will arrange the columns and the rows in a way that's inconvenient, and the individual some of the values in the individual cells might not make sense or might not be formatted according to the way that you want to use them in an analysis you're doing or in an R program that you're writing. And so you need to manipulate these strings that you read in order to get them into a form that you can use them in R, and you can and so that they can be standardized in some way. So I want to reference my notes a little bit here. So the first, there are just a couple general functions I wanted you to be aware of to do with strings. The first function is paste. Paste is like I use paste all the time. It's a very useful function. You can just give paste any number of arguments, and it as long as those arguments are strings or those arguments can be coerced to strings, then it'll just paste those strings together. So, if I give it 3 strings and I say R is great, and I execute this line, it pastes these 3 strings together and gives me the string R is great. If I can paste together multiple strings in a different way by providing a vector. So if I say if I give one string it was the, and then I give I give a vector of strings as the second argument, and I say the first element of this vector will be best, the second argument will be worst, and execute this line. What it's going to do is it's going to take the first argument, it will paste it together with the first element of this vector, and it will paste it back, and it will paste it with the second argument of this vector, and then it will give me back a vector of of 2 strings. The first string being it was the best, the second string it was the worst, as you can see. And I can kind of use this branching behavior in multiple ways. So if I want to paste another string onto the end of these 2 strings, I can provide a third argument that's just the string of times. Can anyone take a guess what this will return? Yeah, so it'll return 2 strings.
It was the best of times. It was the worst of times. Essentially, the off times would be like as though it's part of the. It was the.
Yeah.
And the 2 is how we substituted twice.
Yeah. So it will give you back a vector of 2 strings. The first one it was the best of times. The second one it was the worst of times. Because I gave this a vector as a second argument, it pastes each of these elements in the vector to the first argument, and then since the third argument of paste is of times, it just pastes that one string to the end of these 2 strings that we've created kind of before here. Does everyone understand how that works? If for some reason you have a vector of strings and I should also say that you can so paste has 3 main arguments. Although the first set of arguments is just however many strings you want to provide to the function. Bless you. So I can say it was the. I can say it was the, and then I'm just going to say best. So I'm just giving it. Actually, sorry, I want to say it was the best of times. What's the worst of times? So if I execute this line, it will just give me a single string. That is a pasting together, or another word you might hear is a concatenation of these 2 strings, as you can see. So by default, paste separates strings by a space, and in this result, that is this space. But if I wanted it to be separated by a comma, I could specify this sep argument. And then I just give it a string of just a comma. And as you can see, this space, which is the default, has been replaced by this comma. If I wanted it to be formatted a little bit more nicely, I might want to have a space after the comma. And in that case, I can just add a space after this comma in this sep argument string, and it'll give me comma, and then space as a separator. You can also, if you have a vector of strings, one of my go-to vectors of strings built into R is this variable called letters, which is a vector of just all of the letters of the alphabet as individual strings. So, as you can see, if I did paste, and I gave the first argument as a letter, colon, and then I said letters afterwards, this will give me back a vector of 26 strings, each one saying a letter, colon, space, and then each letter of the alphabet. So if for some reason, if I wanted to, so this letters vector, if we index it, the third element is just the string C. And if I wanted to take this vector of strings and make it into one string so that I had all the letters of the alphabet in order in one string, I could use, I could specify, this collapse argument. This argument takes a string, and the string is just, the string that you provide as the collapse argument is just the string that will be placed in between all of the letters in whatever vector you're specifying as the first argument. So if I say collapse and I just put nothing in this string, it'll just give me, let's see if sep has an effect on this. Sorry, hold on a sec. Okay, so as you can see, if I don't put anything in the string, it will just concatenate all of the strings in this vector together. If I specify a comma, it'll place a comma between all of them. And just to be clear, this can be done with any vector. So if I just create a vector, R is great, and I want to be like very exclamatory about this fact, I could I could specify that they should be collapsed by an exclamation point and then a space, and that'll give me back this vector. Oh, notice that this, whatever you provide to collapse only goes in between the elements of the vector of strings, so I didn't get an exclamation point at the end of this string. Does everyone understand that intuition? Does anyone have any questions about this in general? All right, so yeah.
Does sep also work in the same way?
Sep does work in the same way when you are providing multiple string arguments and not just string arguments in a vector. So if I were to provide multiple arguments, say R is great, and then if I do sep by exclamation point, they will only put exclamation points in between. So yeah, so really the difference between sep and collapse is whether or not you're collapsing all of the strings in a vector, or if you're providing multiple arguments. Like here I have 3 arguments. R is great. Are the 3 arguments.
Why would you use a vector instead of what's the advantage of using a vector?
So the chance is that if you're programming some function that's going to use paste, you will probably be getting data from some other source in the form of in the form of a vector of strings. And so in your program, that will probably be represented as a variable, like in the way that letters is a variable. And so, in that case, if you want to take all of the, in that case, there are 2 things you might want to do. You might want to paste something onto the beginning or the end of all of the strings in your string vector. or you might want to collapse all of those strings in that vector. So in other words, it's very infrequent that if you have some long vector with dozens of elements, that you're going to be like writing out each element and specifying a comma between each element, because you won't be able to anticipate how many elements are going to be in that vector. Does everyone understand what I'm saying there? Okay. All right, so that's really all for paste. There's also just like another function that is very easy to use, you should be aware of, which is called nchar, and that just counts the number of characters in a string. So if I just write the string hello exclamation point and execute this line of code, it will give me back the number 6, because there are 5 characters in hello plus the exclamation point is 6 characters. So that's a very simple, straightforward function. All right, is everyone okay so far? Because we're about to like really dive into something. Okay, so when you're searching through text data or cleaning text data, I kind of already said it, but a lot of the time you'll want to look at a string and look for a pattern or look for a specific phrase, and you might want to replace that pattern with something else. You might want to extract a substring from that string that matches a specific pattern, and this can all be done with a system called regular expressions. Regular expressions as a system and kind of like as a way of thinking about strings exists in many programming languages. Regular expressions actually like exist outside of the purview of programming languages altogether, because it's kind of a concept that was co-developed with linguists, like in the it blends with like academic linguistics, and so here, this is, if you're talking about like regular expressions, this is a comic you like have to show, which Perl is a programming language, and this says if you're having Perl problems, if you've had a few, I've got 90 problems, so I use regular expressions. Now I have 100 problems. So regular expressions can get very complicated very quickly. Hopefully I can show you how to use them in a useful way in the context of cleaning data, but they can quickly get kind of hairy. So the several functions that use regular expressions are specified in base R, like with R out of the box. So there are lots of functions in packages that use regular expressions, and I'll show you one of those packages today. But first, we'll start with base R. So, first, really, we'll start with regular expressions in general, and then I'll illustrate how to use regular expressions with those base R functions. So, in order to do the searching for certain characters in a string or for patterns of characters in a string, you need to be able to use characters to talk about characters. And so in regular expressions, there's this concept of meta characters. So these are characters that you use to search for or to specify other patterns of characters. So the simplest example is that a period meta character represents any character. A star meta character represents any regular expression that precedes it. This just means PE means preceding expression. So the star represents like an expression 0 or more times. And we'll get more into this, but let me try to fold this concept of regular expressions in with the R functions that use regular expressions, I think that will illustrate it better. So there's this function called, there's these two functions that are very similar. One is called grep and one is called grepl. I like grepl better, so we're going to use that one at first. And grepl takes two arguments. The first argument is a pattern, which is a string, and the second argument is a string or a vector of strings that you're searching. So, for example, if we, if we have the string classroom, and we want to search this string classroom for a pattern, let's say the pattern is XX. So the way that grepl works is you provide a pattern. This pattern is this pattern XX just means a lowercase x followed by a lowercase x, and we're searching for this pattern in this string called classroom. If the pattern is found, grepl returns true. If the pattern is not found, grepl returns false. So if I execute this line of code, we'll get back false. Where if at the same time I'm searching for the string class inside of the string classroom, the result is true. And in general, without even thinking about regular expressions, you can think about using grepl where you give it a string as the first argument, and it searches for that string inside of the second argument. So if I specify the string like SRO occurs within classroom, and so the result of this is true. Where, if I specify CLA SSS, and I try to search for that inside of the string, it's false. Does everyone understand that sort of basic functionality? Okay. So this is true in a vector. This works with vectors. So if instead I want to search every string in a vector, we'll do. So if I have these two strings, the first one is classroom, the second one is snow. If I search, I can search both of these vectors, and I will get in return a logical vector. So if the pattern I'm trying to match is just the character C followed by the character L, and I execute this function, I will get back true because you can find CL in the string classroom, and false since you can't find CL in the string snow. But if I look for just the character of O, I'll get back that they're both true because O's occur in both strings. If I look for the string XXX, it's false because this pattern of XXX doesn't appear in either of these strings. Everyone understand that? Okay. So now let's actually try forming some patterns that aren't just looking for literal strings inside of other strings, but actually formulating some regular expressions that could be inside of this, and looking for regular expressions inside of this vector. So one of these meta characters is the plus meta character. And so the way that you use these meta characters is you can form regular expressions sometimes just using meta characters. Sometimes you need to form an expression and then append a meta character onto 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 the end of that expression. So let's just examine this meta character, which is the previous expression one or more times. So an expression that occurs one or more times in both of these strings is the expression S. Just the S character appears in classroom and in snow. So we can specify that. We could just say S, and that will work. But if we were doing something more complicated and we wanted to use a meta character, we could add a plus sign to the end. And because we're in this context of using grep, this grep-L function understands that we're not looking for a literal plus sign inside of these strings. We're looking for the character S. We're looking for one or more occurrences of the character S. So let's add a string that doesn't have the character S, like choice, just to illustrate this. And after executing this line of code, you can see, you can see something that we sort of knew before, which is that there's one or more occurrences of the character S in the first two elements of this vector, but there is not one or more occurrences of S in the word choice. So, I don't know, to get more complicated here, let's say we were looking for, let's see, there's all of these. Let's say you were looking for the occurrence of an S followed by an S. Yeah, let's say you were looking for the case of only a lowercase s followed by a lowercase s. So in this case, we'd be trying to exclude snow and choice. So you can specify exactly the number of times that you might be looking for an expression, and you can do that with these curly braces. So as you can see here, the notation here is the previous expression exactly an x number of times, and we can write that as a regular expression by saying s, and then saying curly braces 2, and so this will only match exactly 2 occurrences of the letter S. So if we run this function, you can see that we get a match for the first element and not the next 2 elements. So that's sort of the general idea for how these things work. I'm trying to think of some other examples that I might be showing you. If we get into, we can get into sort of more complicated examples. For example, let's say that you have, let's create some fake data. We'll just call this vector numbers. And, or really we should call it potential numbers. And let's say that we want to write a regular expression that identifies what elements of this vector, potential numbers, which will be a vector of strings, which elements are phone numbers. So in here we'll put banana, and then I'll just make up some phone number. And maybe, since this is a dirty data set, these phone numbers are like these phone numbers are formatted several different ways. So maybe they have this maybe they're formatted so that they have hyphens in between the area code and so forth, or they don't have any hyphens, or let's just leave it to those. Let's leave it to those two. But let's say so these are 9. These are exactly 9 numbers. So let's say that you have other numbers in there, that, and other just other strings in general. Just to add some noise, some variety. Okay, great. So I'll store that vector inside of this variable called potential numbers. So now we have a real problem. We have all this. We have this data. You can imagine a situation where we have thousands of rows of this data, and we know by looking at the data, looking at the raw data, that phone numbers are formatted 2 different ways. One way with hyphens and one way without. And let's say that we just know that we can be sure that if there are 10 numbers in a row with no hyphens or anything, then it's a phone number. But if it has hyphens, then if it has hyphens and it has this many numbers, then it is a phone number. Oh, so we should let's add something with hyphens. That's not a phone number. And let's add something. Let's add a string with more than 2 hyphens. Okay. So now we want to start thinking about how to form a regular expression for this, to extract the phone numbers, of which there are only 2, out of this vector. So what I do, because to be honest with you, I either don't have a lot of these meta characters memorized, or in order to be sure, I'm always looking at a set of meta characters, just for reference. So we know to start out. Here, let me get rid of this. Or actually, I'll let me move this around. So we know to start out. So we're going to use grepl. So that'll tell us. That will tell us true or false which elements of this potential numbers vector contains a phone number. So the data we're going to be using is these potential numbers, and the regular expression we have to form in the beginning. So we can just start throwing regular expressions against this series of quasi-random strings, and you can sort of see the effect that they have. So if I just specify a period meta character, so I'm not looking for an actual period, you can see that one occurrence of this period meta character, which specifies any character, there is at least one occurrence of any character in all of these strings. Then if I try to look for, so something that we might want to start off with is that we know that phone numbers are formatted in one of these 2 ways. They have these hyphens or they don't. So we can start off the regular expression by saying that which of these strings start with 3 numbers. So let's take a look at our meta characters and try to figure out a way to specify that. So we can specify the numbers see this meta character that shows you use these square brackets, and you can specify any characters within a range. So, for example, we'll kind of take an aside here. For example, if I use that exact pattern where I use these square brackets, A through Z, and then if I just specify letters, so remember this letters variable is a vector of all the letters of in the alphabet. You can see that it's true for all of these vectors. It's true for all of these strings that some character in the range between lowercase a and lowercase z occurs in one of these vectors. But if we cut this off, if we just say, from A through H, and then we go to look through the letters, after H, after H, that we get the result of false because we've only specified characters between A and H using this notation. If we, we could do something where we could make. Sorry, we're going deeper into this aside, but if we could make a vector of like multiple occurrences of the different letters of the alphabet. So we'll call this soup. And so if I go ahead and paste together letters twice, we get this vector of strings with spaces in between each letter of the alphabet twice, which isn't really what I wanted. So let's make sure that these are separated by nothing, by just an empty string. And then what I really want to do is create a vector where the first part of the vector is all of the letters of the alphabet once, and then the second part of the vector is all the letters of the alphabet twice. So we can do that using C, and so this will make a new vector of just all the letters once and then all the letters twice. And you can see that here. So now let's say that I wanted to look for all of the strings in this vector that are only in the range that contain characters that are only in the range of A through H, and only contain those characters twice. I could go back here and use my A through H code, and if you see, if I use this function on our soup vector, I'll get back this vector of trues false because the characters A through H occur in the elements of the soup vector that have H twice, G twice, etc. But if I only want to get the characters in this vector, or the strings in this vector that contain this pattern of any of the letters in the range of A through H and only twice, I can use the curly brackets and specify that I only want it twice, and then it will only give me back true for the corresponding elements that have characters A through H and only twice. Does everyone understand this? That was a lot. So now let's go back to our problem of extracting phone numbers from our potential numbers up here. So we know that we know that all of the phone numbers start with 3 numbers. So if we use grep L, and we really will go back to this expression. Just comment this out in case anyone tries to run this. So here, I always forget to do that, but we're so we're back to this expression where we're forming a regular expression just to see which of these strings begin with three numbers. So if we're looking at our meta characters, there's a meta character for the beginning of a string. So we'll use that meta character, and as we're going through and building this regular expression, I'll execute this line of code, and we'll kind of see what gets eliminated the more elements we add to this regular expression. Or really, what I should say is the more expressions we add to this regular expression. So if I execute this line of code, it's all true because they all contain the beginning of a string. That makes sense. Right, does everyone understand that? To quickly provide a counterexample, if let's say if you were looking for a string that you could specify, you could create a regular expression that you wanted like the beginning of the string and then the letter A, and then if you search through a vector that had the word apple and the word pear, and the word, this is not a wonderful example, the word, I don't know, just something where you have A in the string but not at the beginning of the string. Does anyone have a guess of what, when I execute this line of code, it's going to return a logical vector with three logical values? Does anyone have a guess at what those logical values are going to be? Yes. Does everyone see why that is? Okay. So I get back true, false, false. So that's just sort of demonstrating the usefulness of specifying the beginning of a string with this meta character. So we want to start with the beginning of a string. Wonderful. And then three numbers. There are a couple ways to specify any three numbers, but the way that I like to do it is to use the square brackets and to say 0 through 9 in the same style that we were specifying all the characters between A and H. We can specify all the characters between 0 and 9, and we want exactly three of those characters. Well, actually, let me just, before I even add that, so right now we're looking for beginning of a line and starts with any of the numbers between 0 and 9. So if we execute this line of code, we can see that this eliminates some things, like it eliminates banana. We can look exactly what it eliminates by using this result to index into this potential numbers vector. And so as you can see, all of these strings begin with one number. And so we eliminated banana and we eliminated this is great. All right, so we've narrowed things down. We haven't eliminated anything that we haven't eliminated either of the two phone numbers that we actually need to extract. So we're on our way. Yes.
So when you put the grep L after potential numbers, it creates a new vector with the ones that are true. But you should just now returns the original values.
Yes. So it returns when I just use this. You're talking about this line.
No, the next one.
Oh.
Save that as something else. Now can you? When you say eliminate, it's still false true, right? You haven't actually taken it out of the potential numbers.
Yeah. So I haven't. So if I just examine potential numbers, I haven't taken it out yet. All I'm doing is you can index a function using false and true values. So if I have, you can not a function. You can index a vector using false and true values. So if I just come up with a vector called vect and I give it something really simple, 2, 3, 4, and I want to index into this, I can use another vector to index into this vect vector. So vect is just the numbers 2, 3, and 4. Then if I made up some logical vector like true, false, true, for every element of this vector I'm using to index into vect, for every element that's true, it will return the corresponding element of vect. So I get 2, 4. And so that's exactly what I'm doing in this line, is that this expression gives me a logical vector, which is this vector, and then I'm using that vector to index into potential numbers. But I haven't changed potential numbers. So we're on our way. So the next thing that we can specify is that we want exactly 3 numbers. And so we can do that with curly brackets according to our table of meta characters. I also want to mention that these are not all of the meta characters that exist. These are just very common ones that are immediately useful, and across programming languages, they have the same syntax, where if you kind of get into more complicated meta characters, there can be variations, but these are also the most applicable ones, so you end up being all right. So we're going to use the curly braces to specify exactly the number of times we want to see this expression, which is any character between, or any digit character between 0 and 9, and we want to see that 3 times. So then when we run this line of code, we get back a different different logical vector than what we had before, and you can see that in the difference between what we eliminated from this first regular expression. Then if we add specifying that we only want 3 numbers at the beginning, you can see we eliminate even more possibilities, because these 2 elements only have 2 numbers, or they have less than 3 numbers at the beginning. But we're still we still don't have a perfect solution. So the next thing that we want to be able to specify is you can have a hyphen or no hyphen. So you think to yourself, how do you specify having 1 of something or having 0 of something? You go to your table of meta characters, and the question mark meta character will specify that the previous expression should happen 0 or more times. So the expression that we're looking for is just this hyphen, and we want that 0 or more times, so we'll add a question mark. And as you can see, that shouldn't eliminate. So from what's left in this vector, it shouldn't eliminate anything. But this is just kind of how it's going to go. I'm gonna keep adding counterexamples to our potential numbers vector. So you can imagine a situation where you have some random string that starts with 3 numbers, and then I'm trying to think of the contrapositive of this. I'll think of a better example. Let's just move on. So this, since you can either have 0 or 1 hyphens, this isn't going to eliminate much, since having 0 hyphens is perfectly okay. As you can see, once I add this, once I continue this regular expression, we haven't eliminated anything, though there could be strings in there that we do potentially eliminate. And the next pattern I want, so we've taken care of this case where we have 1 hyphen. And then the next pattern I want is another 3 numbers, which is true in both of the cases of our phone number. And so I can just borrow this expression that we used before where I want the numbers 0 through 9 exactly 3 times. And so this is going to eliminate some things. If I execute this, we only get 2 true elements of that resulting logical vector back. And if I use that logical vector to index into potential numbers, I get back both phone numbers. Now, of course, this regular expression isn't sufficient for all of the possibilities of a phone number. For example, if we had a number, actually, I thought I had an example like this. Oh no. Okay, so let's add kind of something that will interfere with the regular expression we formed, like a regular expression that has, or like a string that has 11 numbers. Here, I think. Great. So if we add that to our potential numbers, as you can see, we still have one character that's not a phone number, and so we would go on to try to eliminate that possibility, and so this is this is just sort of to illustrate like the danger that you can get into with regular expressions, because you might have one data set that doesn't contain a string with 11 numbers all in a row like this. And so you would create this regular expression, you would eyeball the data and see that all of your data is formatted, and looks like a phone number. But that's because of the properties of that data set. If you then use that in a function and you went to go apply that function to another data set where there were sequences of 11 numbers in a string, that program would think that this is a phone number when really it's not. Whenever you're it's a very common situation that you're looking for something that is formatted in that has a couple kinds of standard formats, like an email address or a phone number or an address. And in that situation, I recommend that you go online and take regular expressions, with people's permission, but people mostly give them away, that have been tested in the field for extracting phone numbers or extracting email addresses or what have you. Yeah.
Can you just kind of walk through like the conditions that you placed? Okay, so starting with 3 numbers, and I'm not very sure what the hyphen question is.
Sure. So I'll step through every one. So this caret specifies the beginning of a string, and then the beginning of that immediately following the beginning of a string, there has to be a character, a digit character between 0 and 9. That's what these square braces then 0-9 represent, so any number between 0 and 9. The curly braces then with the 3 in between them represent that there have to be exactly 3 occurrences of one of these digits. The hyphen is not a meta character. It just specifies the existence or non-existence of a hyphen. So if I did grepl hyphen and I was looking through a phone number, you would see that it was there. And if I was looking for like a certain number of occurrences of this hyphen, I could specify that also. So like the thing is that the question mark in this situation is not very useful because a question mark just specifies that something should occur 0 or 1 times. So in most in like the most general situation, it occurs 0 times, and so it doesn't even matter to have that regular expression, except in the cases that it occurs once. So, for example, if I didn't specify that this hyphen could occur 0 or should occur 0 or 1 times, let's just look at the situation where we're dealing with both of these phone number formats, where either it has hyphens or it doesn't. So if I grab this phone number and I grab the beginning of this regular expression, let's say that I say it has to have a hyphen, so I don't specify the question mark. This first phone number will be valid, and the second phone number is not valid. So by using the question mark, I can broaden this regular expression so that both of those strings are recognized as valid phone numbers.
And that's saying that if you didn't have a question mark, would you have to have a hyphen immediately after the first 3 digits?
Yes. If I didn't have the question mark, I would have to have the hyphen immediately after the first 3 digits. Yes. And then I would lose all of the phone numbers that don't have hyphens. Does everyone understand that question? All right. Okay. So now that we have like a basic understanding of regular expressions, there are several. We'll keep using these phone numbers as an example, but there are several functions in R that you should be aware of for using these regular expressions. For example, we know about grepl, so that just returns a logical vector of whether or not a certain expression exists within a string or a vector of strings. There's also grep, and grep just returns the indices of the vector that's provided as the second argument that for every index that contains this regular expression. So this is the beginning of our phone number regular expression, and I'll add a banana to this. So if I just use grep, I'll just get back a numeric vector of 1 and 2. But if for some reason I'm not looking for this regular expression, but I'm looking for NA followed by the money sign meta character, which specifies the end of a string, then I just get back the number 3. And so, this is obviously, you can use this for indexing also. So if I stored this as a vector we'll call text2, and I want all of the vectors in text2 that end with, that the end of the string is NA, this will give me back a numeric vector with all of the elements that match that regular expression, and then I can use that to index into this text2 vector, and that'll just give me back banana. Two other strings you should be aware of are, two other functions that deal with regular expressions you should be aware of are the sub function, and which goes hand in hand with the G sub function. Yes, sorry.
Does these meta characters go before or after the specific characters?
Sure. So the way that it works is that you specify an expression, and then you kind of use those meta characters to say something about that expression. So usually after.
Oh, but why is the caret sign before the condition?
Yeah, so the caret sign is a meta character and just represents the start of a string, and so that is a meta character that doesn't go after because it's impossible. It's impossible to have anything before the start of a string or after the end of a string. If you made a regular expression like a and then the beginning of a string, that won't ever match any string. Um, uh,
That varies by the meta characters.
excuse me.
So like what are so it depends on that meta characters whether the expression comes before or after.
Yeah, that's a really good question. I'll annotate this table so that there'll be a third column that will provide details, and that will include if it should become before or after or can do either. That's a good question. So sub and G sub take three main arguments: a pattern, which is a regular expression; a replacement, which is a string; and X, which is the string that you're searching. So if I am looking for the pattern AN, and I want to replace AN with a capital X, and the string that I want to replace every occurrence of AN I want to replace with an X is the string banana, then sub will replace the first occurrence of AN within this string with an X, as we can see. It just kind of takes the first AN out and replaces it with an X. G sub takes the same arguments, but G sub will replace every occurrence of AN with an X. And so I just get B capital X A back as a string. At the same time, if I wanted to replace every A or N individually with an X, I could use G sub, and I could specify the regular expression of A or N. I could also specify, here, let me just make sure that this works. I could specify the regular expression of A or N. This is using the pipe character, which is usually above the backslash key. If you hit shift backslash on your keyboard, you get this pipe character. So I'll replace every instance of an A or an N with an X in banana. So it's just going to be X, X, X. Another way you could formulate this regular expression is, instead of using the or meta character, you could specify a set of characters using the square brackets. So this will replace any character in the square brackets with X. As you can see, if I added a B to this set, it will just replace everything with X. Does anyone have any questions about sub, G sub, and doing this replacement? Okay. So one of the most user-friendly R libraries that I think you should know about is this library called Stringer. If you do install packages string R, you should all run that line of code, and that will get you the string R package. If you have any problems, let me know, and I'll come help you, because sometimes there can be issues installing it. But I'm going to load the string R package using the library function. and then string contains just like a menagerie of useful string functions. Which I have a list of, but they're not online. I don't know why. Okay. So all of the, or most of the useful string functions in string start with str underscore, and then as you can see, if you're using RStudio, you can access them pretty easily using using autocomplete. But there are simple. Most of these str functions have exactly two arguments that follow this convention of the string that you're looking through, or the string that you're trying to find something out about, and then a pattern, which is another string and is usually a regular expression. So if you want to count the number of substrings inside of a string, so let's say the string is banana, and the pattern is an, you can see that the string an occurs twice in banana. The string a occurs 3 times. An a or an n occurs 5 times, and so on and so forth. Yes.
If this stringer is not available for the version, how do you update the version?
If you do, hold on a second. There's a better way to do this. It's like r version string. There we go. Yeah, if you do r.version.string, what does it say? And like, what it says 3 point what?
Like 2.3, the same thing.
Oh. Let me see. Let me see if it gets upset with me.
Oh, maybe I wrote it. No, sorry. I wrote it wrong.
Oh, okay. No problem. So, does anyone else have any questions, or did everyone get? Can you raise your hand if you didn't get it installed? Okay, wonderful. So sure, so like that's this is just a tour of string R. String detect will takes the exact same style of arguments. In fact, we can use these arguments again, and this will return true or false if it finds this pattern inside of the string. I had to restart R, so as you can see, the regular expression of A or N is in there. Capital X is not in there. String, here's an interesting one. String duplicate. This is, with string dupe. Let me see if there's better examples of this actually. With string dupe, you could use. This is similar to rep, where you could say like rep the string, banana 3 times. It'll give you a vector of banana, banana, banana. With string dupe, you can. Yeah, let me just try the exact example that it gives us. So here we're creating this vector, apple, pear, banana. If we do what string dupe will do is it will concatenate each element in this vector the number of times that you tell it to. So like the first element I think will be apple, apple. Yeah. So to do the string duplication, you give it a vector of strings. You specify a number of times that you want each element repeated, and it will give you back a vector of strings with that number of repeats for each element. These vectors like string extract and string match. String extract will, given given a string and given a regular expression, it will extract a substring. This is actually a very useful one. So if I have banana and I specify the regular expression of a or n exactly 2 times. Does anyone have a guess what I'll get back will be a string? Does anyone have a guess of what that string will be? So string extract takes a string, takes a regular expression, and extracts from that string the first occurrence of that regular expression. So we've got this set of characters, which is a or n, and so exactly exactly either of those characters 2 times.
Because it's going to be BA left over, or is it going to be those two? So it's going to be A and A N?
So it extracts. So what it does is it extracts the substring. So whatever is specified by this regular expression is what we'll get back.
Oh, okay.
Yeah.
So it's A and A N, or is it going to be A and A?
So I believe it's going to be just an, because it's 2 occurrences of either a or n.
Oh,
Where if we said
that makes sense.
3, if we said 3, what do you guys think it would be?
A and
Does everyone see that? Okay. Where if we let's see here. Yes.
Does the tree specify that the extraction happens twice of A or N?
So the 3 specifies. What do you mean by the extraction happens twice?
What does the 3 mean?
Sure. So the 3 means exactly 3 occurrences of either a or n.
So why don't you have the max then? If it's A or N? You don't have a formula to put that, or not the backslash, but the vertical line to distinguish that it could be A or N.
Sure. So I think that should work. I think if you say a or n, whoa. Oh no, because this is saying either a. So it kind of depends on like this. It depends on the ordering. So I think if we said this, it would work. Yeah. So if you say a or what this regular expression means is either a once or n exactly 3 times. So n 3 times doesn't occur in the string banana, but a once does. So what we get back, it extracts whatever this regular expression matches. So we get back just the string a. Where if I put this in general, you are like generally safe putting things in brackets and leaving and leaving meta characters in those brackets. So this is the equivalent of this, but specifying these brackets makes the exactly 3 times apply to everything in the brackets. Where if I wanted to say, if I said A and B exactly 3 times, then what would I get as the result of this? So just to be clear, the order of what's in these brackets doesn't matter. This is just specifying the set of characters A or N or B. If I wrote BAN or NBA, those are all what's inside the brackets in all of those cases is equivalent.
Would you get BAN?
Yes, so you get BAN back, I believe. Yeah. So, I had a good example. So let's say here's an example of a kind of meta character I haven't showed you yet. So in the way that you can specify any characters within within a set of brackets. You can also specify all of the characters except the characters within a set of brackets by using this caret inside of the brackets. So this has nothing to do with the caret that specifies the start of a string, but a caret inside of the square brackets has this special meaning, meaning anything that is not in any set of characters that is not in the square brackets. So, for example, if I run this, I believe this will just give us back B. And it does. This is anything, any occurrence of N or A is excluded. So that's string extract. Anyone have any other questions that I've missed? String split is an interesting function, a useful function. Again, it's you specify a string and a pattern, but it will, every time that pattern occurs inside of the string, you will it will kind of like it will take apart that string so that you get a vector of strings in return. So if I have the string R is great, each word in this string is separated by a space. And so if I use the very simple regular expression of just a space, I mean, this isn't much of a regular expression, this is just a character, I'll get back a list, which is denoted by this notation. It's a list that contains one element, which is this vector of strings. So, to extract an element from a list, we can use the double brackets. And so then this is just a vector of 3 strings. R is great. And, we can index into that and get the second element. It's just that the string is. Does everyone understand that? The reason it returns a list is because you can get into there are complicated examples where you might have multiple vectors, and so in order to store multiple vectors, each vector is an element of that list you get in return. And yeah, the remainder of these functions in string are really just like for convenience sake. So there's all these str2 functions, and this actually happens a lot of the time where, at least in my experience cleaning data, where you have 2 fields. Like for example, a classic example is that you'll be like dealing with postal information and addresses, and you'll have some addresses will have like the state as GA. Here we'll make this postal states. Some will have in some of the rows the state abbreviation will be GA, and others it'll be capital GA, and the same with lowercase md and capital MD, and you want to standardize all of them. So you can use string to upper, and we can provide this vector of postal states. And it will capitalize all of those state abbreviations. In the same way, you can use state to lower. That'll do the same thing, but it will make them lowercase. If you are dealing with strings with titles, it's like if you're cleaning up a movie database, a lot of people like analyzing movies to create recommendation engines and that kind of thing. So if you've like gone with the wind for some reason, it's formatted badly, and you use string to title, it will give you this title case, which I guess actually isn't that smart, since like in very formal title case, the T and the should be lowercase, but you get the idea. Let me see the rules. No. All right. And then this is another function I use all this time is string trim, which you'll read in some Excel spreadsheet, and for whatever reason there'll be all kinds of white space around the cells, so you'll have some piece of information. It will just be like surrounded by a lot of space, and you want to make some and it's not uniform space, so like so there are differing amounts of white space on both sides of strings that are the same, and you want to standardize them all. You can use this has to be a vector. You can use str trim to just get rid of surrounding white space. All right, so that concludes our talk about strings. Does anyone have any questions about string R? Regular expressions is like, again, this is kind of like a tip of the iceberg look. There's a ton that you can get into with regular expressions, but I feel that they're an essential tool for cleaning data, and for cleaning data sort of systematically, so that you can write a regular expression once, you can write a program once, and then you can use that program on multiple data sets in order to clean multiple data sets. And in the next hour, we'll get into that a little bit, I hope. So if no one has any questions, I'm going to pause this, and we'll have like a 3-minute break.